This presentation explains two sections from the Machines and Mechanisms MIDI project. Problem 1. A spool of rolled sheet metal rests on a truck bed. As the truck accelerates, friction causes the spool to translate and rotate simultaneously. Free-body kinematic and kinetics diagrams were developed to analyze the system using Newton's second law and rotational dynamics. These are the known parameters, unknown parameters, and subtask 1, subtask 2, which was no slip, slip, or no slip. The governing equations were used to calculate angular acceleration, center acceleration, and friction force. A rolling constraint equation was applied for no-slip conditions, and friction check determined whether slipping occurred. This is a summary table of the slip and no-slip results. These are the different scenario results for the MATLAB analysis. The derived equations were verified using MATLAB and Simulink, and the outputs closely match the hand calculations. The results showed that increasing truck acceleration increased the required friction force, and once the required friction exceeded the maximum static force friction, slipping occurred, as seen in these diagrams. The parametric analysis also showed that reducing the friction coefficient caused slippage, while changing spool mass did not affect the slip condition because mass cancels out from the friction equation. These were the different values for each scenario. The oscillation graphs also showed that the higher truck acceleration increased spool acceleration and caused the measured motion to diverge from the no-slip prediction. The MATLAB results matched the theoretical calculations with less than 0.1% error, validating the model. The second section investigated a pendulum impact virtual lab involving block sliding and tipping behavior. These are the three different free-body diagrams, kinetic diagram and kinematic diagram. These are the known parameters, unknown parameters. The governing equations use energy conservation, friction equations, and Newton's second law to determine the post-impact motion. This was the no-tip case and situation. MATLAB analysis. MATLAB simulations verified the theoretical calculations and analyzed the different experimental conditions. The results showed that lower pendulum mass reduced block displacement, while increasing impact height increased the turning moment and caused permanent tipping behavior. The overall assumption was that changing the pendulum mass changes the impact force transferred to the block. A larger pendulum mass produces greater momentum and impact force, causing greater block displacement and motion responses, as seen in these graphs. The results in task 3 showed that the kinetic coefficient was 0.3. The comparison showed that increasing the impact height changed the block response from simple sliding to permanent tipping due to the greater turning moment created. Overall, the MATLAB simulations successfully verified the theoretical equations and demonstrated how friction, impact force, and impact height controlled sliding and tipping behavior. Thank you.